Greetings to all and welcome to this lecture. So, we are going to discuss the module 2 two-terminal MOS structure. In this lecture number 2 of module 2, we will discuss about potential and charge balance. We will discuss what will happen when the oxide fixed charges are coming into picture. In the sense, in the last lecture, we have seen that the flat band voltage is the voltage which is externally applied into the MOS structure, which actually counterbalance the charge pileup into the semiconductor, and hence the band will be flat. But in that condition, we assumed that the oxide is ideal. Here we need to see what will happen if the oxide is non-ideal. Then we will discuss a bit about what is the concept of effective oxide thickness, and then what will happen if a potential is applied in a two-terminal MOS structure which is given as metal, oxide and semiconductor. So, we will see when the external voltage will applied between metal oxide semiconductor structure between gate and body, then how the charge and potential respond with this structure. So, let us say this is VGB and what is the potential and the charge balance here. These are the learning outcome of this lecture, which will give you an idea about EOT or effective oxide thickness, which gives you the idea of flat band voltage under the influence of contact potential as well as the oxide charge, and how the potential and charge balance equation can be written or solved in MOS capacitor. Let us do a quick recap. In previous lecture, we have seen that when two different materials are coming in contact, then there will be a charge transfer under no bias. That charge transfer is due to the work function difference of the metals. So, there will be a contact potential coming into picture when these two materials or two metals will make a contact, and this contact potential is given by the difference of work function of two different materials. We have also argued that what will happen if different materials will be in series. We found that the potential psi k L, meaning the potential between the M1 and M1, M1 and Mn is nothing but the potential psi k L, and that would be given as the work function of metal Mn minus the work function of metal M1. It stands for no matter how many materials will be in series, the equivalent contact potential is nothing but the last metal work function minus the first metal work function. We also argued on that, can we measure this contact potential by a common voltmeter? We have taken an example of PN junction diode, and we said that when you want to connect the built-in potential of a PN junction diode, you cannot simply measure by a voltmeter, because the contact potential formed at the P side and N side is exactly counterbalancing the built-in potential formed between the junction, which is psi Bi. We have also seen that what will happen if a battery is connected or a battery is coming into the loop of these connections. Then yes, the reading will be nothing but V source, and we can measure the voltage of that battery or the voltage source by a common voltmeter. We apply these analogy or these understandings or the contact potential in our MOS structure. We said that we have simple layered structure, metal oxide and semiconductor, and due to the difference between the work function of metal and semiconductor, there will be a charge transfer if it is connected with an external wire, considering the oxide is not leaky, because if the oxide is leaky, there will be a charge transfer through the oxide also. But we are just considering in an ideal way that the oxide is not leaky. So, to have a charge transfer in the structure, we need to connect between gate and body, or we need to connect a gate and body through external wire. When you connect the gate and body through external wire, there will be a charge transfer, and that charge transfer is actually due to the work function difference between gate and body. We said that if we applied a voltage source externally in such a way that this charge transfer can be stopped, that is called a flat band voltage, which is nothing but phi ms. It means the difference between the work function of metal and semiconductor. In that condition, or in that analysis we assume that there is no charges available into the oxide. So, we consider that the silicon dioxide layer is just ideal one. But is it the only way that contact potential can cause a charge pileup into the semiconductor? So, answer is no, because the oxide layer is not always ideal. It is like you take a single silicon sheet or silicon wafer, and when you expose this with an oxygen ambient, then what will happen? The silicon dioxide is thermally grown over it. The silicon is a crystalline structure. We all know that from our basic fundamentals, and it having a 4 bonds. It forms a 4 covalent bonds. So, what will happen when you exposed the silicon wafer with a very high temperature of, let us say, 900 degrees centigrade? At that moment, the oxygen will react with silicon, and one oxygen atom will react with 2 silicon to satisfy its bonding. Or we can say, in terms of silicon, one silicon is actually covered or related or make a bond with 4 half of the oxygen atom. So, though this picture seems that silicon dioxide is a crystalline structure, but it is highly amorphous. So, what will happen when a silicon dioxide layer forms over the silicon? So, let us consider this is silicon and this is silicon dioxide. In that condition, what will happen? Exactly at the interface. So, exactly at the interface there are possibility of few charges available into picture, that is called oxide charge. Broadly saying, these oxide charge are classified as oxide fixed charge, oxide trap charge, mobile ionic charge and interface trap charge. So, what will happen when you expose the silicon with a high temperature? Then there might be a possibility that there will be oxygen vacancy, meaning just a small bit above to the silicon dioxide layer, because when you grow silicon dioxide, deep in the silicon dioxide it is a pure silicon dioxide, but near the silicon dioxide interface, what will happen? There might be SiOX formation, where X is not 2, it is not an ideal silicon dioxide or a pure silicon dioxide structure, it is this X lies between 1 and 2. At that condition there will be an oxygen vacancy, meaning the silicon atom will leave an electron from here, thus it becomes positive. That is what the oxide fixed charge are always positive in nature. They found in general a bit above than the silicon dioxide interface, and hence it is not dependent on what is the thickness of silicon dioxide layer, what is the doping on silicon and all. There are other type of charges which are called oxide trap charges. So, when you put a very high radiations or high stress into the silicon wafer while doing fabrication, then there will be some kind of charges coming into picture, that is oxide trap charge. Another kind of oxide charges are mobile ionic charges. These charges are coming like handling the wafer, alkyl ions and all. But to be very clear that in recent days, when the fabrication facilities are very mature enough, these kind of charges are highly reduced. Interestingly, there are another type of charge carrier which is interface trap charge, meaning you have a silicon dioxide, and exactly at the interface what will happen? So, if I show you like this, you have a silicon wafer. So, one silicon atom, another silicon atom, another silicon atom. These silicon atom make a covalent bond with the 4 neighboring silicon atoms. So, let us consider this is a silicon atom which is of our interest, and this is measuring. So, this is A and making a covalent bond with the neighboring atom. So, one like this. But what will happen to the top of the silicon atom? So, when you dice the wafer, what will happen? Some of the silicon atoms will get cut off. That is called dangling bonds. Due to these dangling bonds, there is some kind of charges are coming into picture exactly at the silicon dioxide interface. That is called interface trap charges. These trap charges can be positive or can be negative. All in all, as of this course is concerned, what we'll consider, we will consider all type of charges as nothing but Q naught, which is considered as a fixed oxide charge into the silicon dioxide, and we'll consider always it will be in positive in nature unless stated otherwise. Now we'll see what is the influence of these positive oxide charge in our MOS structure. We will revisit our flat band voltage condition, where we claimed that when two metal and semiconductors are connected with some external wire, then because of the contact potential there is charge pile up into the semiconductor, and hence we applied a voltage source externally with a value of 5 ms such that there is no charge pile up into the semiconductor. In that condition we assume that silicon dioxide is ideal, but here if we consider the silicon dioxide does have some trap charges, then what will happen? So these square boxes represent my Q naught. This is oxide charge. Because of this positive oxide charge, there are some negative ions or negative charge come into the semiconductor and some negative charge come into the metal plate. We wish here to remove these charges present into the semiconductor. So again the question remains same, can I connect a voltage source externally with some value such that these negative charge of semiconductor can be removed? So again the answer is yes. What we can do, we will calculate what is the voltage across this oxide. So this oxide voltage is denoted by psi ox. The capacitance of this oxide is given as C ox, and we can simply use a relation Q equals to CV to calculate the oxide potential. So from here we can see that if we apply a voltage source of Q naught by C ox with a negative sign externally, then these positive lines, the electric field lines from these positive charge will go like this, and hence there is no charge pile up into the semiconductor. As we are seeing this structure in 2D, but in general this is a 3D structure. It's like this is a 3D structure. So this side is actually your area of cross section. So if you want to calculate the overall charge, then you need to multiply with the area. So for the sake of simplicity, in subsequent lectures what we will consider, the charge per unit area, which is Q naught divided by A. Again, to give a particular notation, we will use Q naught dash. So wherever the dash is coming up, it is meaning it stands for per unit area. Similarly, to satisfy the equation, we need to take C ox per unit area, which is what? COX dash. So by this argument, we can say that we can connect a battery with a value of minus Q naught by COX dash externally such that there is no charge coming into the semiconductor. This value of battery or this value of potential is need to be added in the definition of flat band voltage. So in general, the flat band voltage is given by phi ms minus Q naught divided by Q naught dash divided by COX dash. This is the overall definition of flat band voltage. So let me revise that the flat band voltage is a voltage which requires that there is no charge pile up into the semiconductor, and hence the band should be flat. So not only the contact potential playing an important role, rather the oxide charges are also causing a charge pile up into the semiconductor. So we need to connect an external battery in such a way that these charges are not coming into the semiconductor. Here we need to define some parameters like oxide capacitance. COX dash is can be given by epsilon OX dash divided by TOX, where epsilon OX dash is the permittivity of oxide, which is nothing but epsilon naught into epsilon of oxide. So where epsilon naught is a relative permittivity, which is 8.854 into 10 to the power of minus 14 farad per centimeter. This TOX is the thickness of semiconductor oxide or silicon dioxide. Now, is it mandatory that we will make the silicon dioxide in our MOS cap. In the previous lecture, we said that in recent devices, the silicon dioxide is no longer the only possible oxide layer. Rather, we are using a stacked layer of silicon dioxide or of gate oxide. That layer comprises some high K dielectric such that the physical thickness of oxide layer will be improved. What happens is, when you actually follow a scaling rule, then it is not always true that you can scale with some only one dimension and other dimension left untouched. You need to scale the device thoroughly, and that actually pushes the limit of silicon dioxide scaling limit. So, if you scale the silicon dioxide to a very thin value, then what will happen? There will be a gate leakage or dielectric breakdown. To avoid that, we will replace a silicon dioxide with some other material which having a physical thickness higher, and it will give the equivalent oxide capacitance same as silicon dioxide. That is the concept of effective oxide thickness. Let me explain this effective oxide thickness with an example. For example, I am considering a silicon dioxide is completely replaced by another material. Let us consider HFO2, which is hafnium dioxide, and that hafnium dioxide is replaced with a 5 nanometer thickness. So, what is effective oxide thickness if a complete silicon dioxide is replaced by HFO2? So, the physical thickness of HFO2 is 5 nanometer, but what is the equivalent thickness a silicon is experiencing because of this 5 nanometer thickness of HFO2 is called effective oxide thickness. So, using this formulation, we can calculate what is the effective oxide thickness. So, EOT is nothing but the thickness of insulator, which is here in this case 5 nanometer, or HFO2 of 5 nanometer. So, 5 nanometer. Permittivity of the silicon dioxide, which is approximately 3.9 times of epsilon naught, and permittivity of insulator, which is lies between 16 to 34. So, you can take 22, for example, 22 times of epsilon naught. When we solve this, we will get 0.88 nanometer. This is the actual meaning of effective oxide thickness, meaning you have grown oxide HFO2 of 5 nanometer. So, the physical thickness is 5 nanometer, but the equivalent thickness which actually silicon experiencing, right, is 0.88 nanometer. Let us solve a small example. So, consider a stacked gate oxide with an EOT of 0.0 nanometer. So, in this case, I have a stacked oxide. Let us say this is silicon dioxide and another layer of HFO2, and the EOT, the effective oxide thickness of these two layers is given as 0.9 nanometer. So, this is my EOT, right. Given that the thickness of silicon dioxide layer is 0.6 nanometer, I need to calculate what is the thickness of HFO2. So, thickness of HFO2 I need to find out. By considering the analysis of effective oxide thickness, I can simply write the total thickness of the oxide is nothing but the silicon dioxide layer thickness plus the thickness of HFO2. This value is given as 0.9 nanometer and this is given as 0.6 nanometer. So, I need to calculate what is the thickness of HFO2. Again, this thickness of HFO2 is equivalent thickness. So, let me rewrite as equivalent thickness of HFO2, not the physical thickness we are talking about. Here, it is clear that the equivalent oxide or HFO2 thickness is 0.9 nanometers minus 0.6 nanometer is 0.3. If you see again here, what we got is equivalent oxide thickness what silicon is experiencing is 0.3 nanometer, and I am interested in this thickness. So, you can simply write 0.3 nanometers is equals to T of HFO2. This T of HFO2 is the physical thickness of silicon dioxide into 3.9 divided by 22. From here, if I am going to calculate what is the physical thickness of HFO2 is coming out to be 1.69 nanometers. So, the crux of the story is the total thickness of the gate oxide is 0.6 nanometer plus 1.7 nanometer, which is 2.3 nanometer. This is the physical thickness, but the actual thickness what silicon is experiencing, right, is what 0.9 nanometer. That is what the concept of effective oxide thickness. We will also see, let us see the energy band diagram point of view of the flat band voltage. So, let me draw the energy band diagram of metals and semiconductors separately, and then we will discuss what actually is happening when you apply a flat band voltage. So, for the first case, consider there is no oxide charge into the oxide or silicon dioxide. So, you have a metal, let me draw a reference level. There is a metal Fermi level which is given by phi m1 or phi m. This is Fermi level, this is work function of metal, and we are considering that phi m is greater than phi s. So, I need to make a phi s also, which is with reference to Fermi level. So, this is what is phi s. Around the Fermi level I can build the other energy levels, that this is EI, this is EC, and this is EV. And in between of metal and semiconductor there is oxide layer. In general, so let me make like this. This is the reference level, ER. Now, the oxide energy gap is higher than the energy gap of the silicon. This is EG. That is what we are just showing with some discontinuity, and this is now your phi m and this is now your phi s. So, the moment you connect externally with the wire, what will happen? Because of the work function difference, there will be a charge transfer from semiconductor to metal, and hence the charges will go from semiconductor to metal. This is considered, let us say, p type semiconductor. So, the charges will go from semiconductor to metal and it becomes more positive. So, the bending will be look like this. So, now the Fermi level will get aligned and the bending will look like this, because it become more positive near the surface. You do not want that way bending. That is what you are actually trying to apply a voltage source which actually remove this bending or the charge. So, what you do, if there is an electron flowing out of the silicon, you will connect a battery in such a way like this. So, this terminal of battery is actually repel back the hole to the semiconductor, and it will make the bands flat. That amount is given by phi ms. So, you are connecting an external battery of phi ms which actually blocks the flow of carrier from semiconductor to metal. In addition, what we have discussed, that in semiconductors what will happen, you have in oxide you have a positive charge here. This positive charge is also causes a charges into the semiconductor, which is present into the oxide causes a charges into the semiconductor. So, we need to connect a negative battery of value minus Q naught dash by Cox dash, right. If this is negative, what will happen to the bending? It will be like this, because always the electron potential can be represented by the opposite of the potential energy because of minus sign of electrons, right. So, this can be represented as this, and this band diagram is for Q naught dash is not equals to 0. So, in total you have applied an external voltage VGB is equals to V flat band voltage, which actually tries or helps to make the band flat. So, in this condition, if there is no oxide charge, then the voltage is equal to phi ms, but if there is an oxide charge, then you need to apply VGB is equals to phi ms minus Q naught dash divided by Cox dash. there you take care that about the bending of this oxide, because this bending in the oxide shows there is a potential drop across the oxide as well. So, analyzing after this, we will see what is the potential and charge balance equation in our MOS cap. In our MOS cap, which is a layered structure, so this is metal, this is an oxide, and this is a semiconductor. The moment you connect a voltage out of it, this voltage should follow a potential balance equation, or in general you can say KVL. So, ultimately this voltage VGB should be equal to the voltage drop across the oxide, which is denoted by psi ox, the voltage across the surface, which is denoted by surface potential, and the voltage between these lids, right. So, what will actually happen when you apply a positive voltage into a layered structure of metal oxide semiconductor? When you apply a positive voltage, then there is a positive charge coming into the gate. So, the same amount of charge should leave the other plate of the structure, or you can say the negative charge of that amount will come into the another plate, right. So, if you apply a positive charge, these electric lines will first repel the holes, which is considered as a p-type body, repel the holes back to the body, and hence it will leave immobile ions, right, which is negative. If you go on increase VGB, then this potential is actually pull the electron from the body, which is nothing but a minority charges here. In the p-type body, this N naught is a minority charges, and they are also negative, which means that if you apply a positive voltage here, it causes a positive charge into the gate terminal and resulting in negative charge into the surface. If you apply a potential balance, then VGB should be equals to the voltage drop across the oxide, the voltage drop across the semiconductor, and the total voltage in between the contacts, the gate and the body. So, this is our potential balance equation. Sometimes we get confused what actually psi ox and psi s. So, let me give you an example of a connection of two batteries. Let us consider this is 2 volts and this is 3 volt, and I am interested what is this node A. Let me ask you one question, is the node A positive or negative? So, you might ask with respect to what, because whenever we are asking about positive or negative, we are actually comparing with some other, right. So, if let me tell you this is, let us consider this is node B and this is node C. So, with respect to node B, this A is negative, that is what you are saying, this is voltage of 2 volts. Similarly, with respect to C, this is positive and you are saying this is 3 volts. In total, between B and C, it is 5 volts, right. That is the same case here in surface potential and oxide potential. So, when you applied a voltage VGB, this voltage is nothing but what? Oxide voltage or oxide potential. So, drop across the oxide. So, this is psi ox. Similarly, this exactly at this point, we can say from here to there, this voltage is nothing but what? Surface potential. Now, if you see, if node A is positive with respect to C, what amount of charges will come near to node A? Because this is positive, the electrons will go there, right, because we are talking about metal system. So, electrons will only come, but if it is semiconductor and that too p-type semiconductor, what will happen? A negative charge will come up. So, the surface potential is the potential which is responsible to cause a negative charge into the semiconductor body. This negative charge can be given by immobile ions or the electrons. We will see what will happen when you apply the VGB and in what range this will give what amount of charges. So, in total, the potential balance equation is nothing but whatever be the gate voltage you are applying is exactly equal to the drop across the oxide plus drop across the semiconductor plus there will be a contact potential. Okay, what will happen if you change the voltage? It means you are changing the VGB by some small amount. will the change appear across this phi ms? No, because this is a constant voltage. This is the fabrication parameter. Once you fabricated the MOS structure, then the work function of metal and semiconductor is fixed, and at that moment the change in VGB is only appearing across the oxide and across the semiconductor. So this you can simply say in words that this is nothing but a KVL of MOSFET. Similarly, we need to see what is charge balance equation. So in charge balance equation, the moment you connect a battery, this battery will actually provide a charge into the metal plate, which is nothing but given by Qg, and if we are representing in per unit area, it will be Qg dash. This positive charge is actually causing a negative charge in the opposite side of the plate or in the semiconductor. This is given by Qc. Here C stands for channel. We will discuss later on when we go for a MOSFET, you will get actually an idea about what channel means, right. So this is represented as Qc, and again if it is per unit area, then Qc dash. In addition, we have another charge which is represented as Q naught dash. Here Q naught dash is nothing but oxide potential. So again charge balance equation meaning KCL for MOSFET, which gives that the total charge is should be conserved. So Qg plus Q naught plus Qc should be equals to 0. If you represent in per unit area, it is nothing but Qg dash plus Q naught dash plus Qc dash is equals to 0. Now again the same question, if you vary VGB by a small amount, will the change in Q dash appear? No, because it is a fabrication parameter. So it is almost constant. So when you change the gate voltage or gate to body voltage, the change in charge at the metal plate is exactly equal to the change in charge at the semiconductor. That is what we will get delta Qg dash plus delta Qc dash is equals to 0, or you can write delta Qg dash is exactly given by the minus or the opposite change in channel charge. This is the charge balance equation for MOS capacitor. Let me summarize. In this lecture, we have flat band voltage is given by phi ms minus Q naught prime by Cox dash. So if the oxide is non-ideal and there is an oxide charges present into it, you need to consider that potential drop across the oxide in terms of flat band voltage, which will actually tries or helps you to make the band flat. So this is just a initial case to study of the MOS capacitor when you apply the more voltage, in the sense whether you are applying a voltage positive or negative, what is the implication of VGB on MOS cap. You will actually take a reference, that reference is nothing but a flat band voltage. We have also seen what is the impact of scaling of the oxide thickness, which is considered as EOT, effective oxide thickness. The effective oxide thickness is nothing but a thickness of oxide which actually silicon experiences equivalently, in the sense it is not like a physical thickness of the oxide. Then we have seen that we have a MOS structure, a two terminal MOS structure, and we are applying a gate to body voltage externally, and in the gate to body voltage this VGB is actually dropped across the oxide, which is psi ox, across the semiconductor, which is psi s, and between two contacts. So ultimately the VGB can be written as psi ox plus psi s plus phi ms. This is charge balance equation. In similar way, the potential balance equation can be given by the total gate charge is equals to, or the total gate charge plus the channel charge plus the oxide charge is equals to 0. So charge should be conserved in the system. So okay, we will stop here for today. Until then, take care.